Good afternoon, friends. Welcome to the STP training webinar, the topic for which is solving performance problems with AI. Our speaker for the day is Mark Tomlinson. I'm Smita Mishra, a professional tester myself, and I'm super excited to host you all and Mark on our STP webinars. Quick information for all of you. The next upcoming conference we have is Spring 2019 STPCon, which will be held at San Francisco from April 1st to 4th this year. The program is up for your review, and the topics range across automation, AI, machine learning, DevOps, performance testing, leadership, mobile testing, security, and so much more. And it's raining discounts. As you can see on the screen, there are 1 and 2 days packages on offer. You can note down the discount codes for them. Also, do not forget, you can still have big savings on alumni and team registrations. Should you have any queries, do email them to info@softwaretestpro.com. And if you want to follow the speakers who are going to be speaking at STPCon, you can please tune into STP Radio that our speaker for today, Mark Tomlinson, hosts. And in fact, his very recent podcast has been posted yesterday or probably just today, and it actually we have our keynote there, Jason Arbon, detailing about all his talks, and he's also covering Mark is also covering most of the speakers who are going to be there on STPCon, so I'm sure you'll find that of your interest. All right, coming to you, Mark. I do believe you've been a very regular speaker at STPCon. So
no, this is my first time.
Is it? Okay. So, all right, then very welcome to STP.
Oh, this is great. I'll pretend like I don't know anything about STP, but I do. Cool. I know everything.
Yes, that's very nice to hear. And so did you get a chance to look at the conference program and any selections so far on what sessions and workshops you are looking forward to?
Yeah, I'm actually really lucky because I get to spend time interviewing a lot of these people. So I study their abstracts, I dig into kind of the details, and then the fun thing on the podcast is we get to ask some of the speakers like what inspired them about the talk they're giving or the workshop they're teaching. So it's been really enlightening. And I will say this talk that I'm giving today on AI was inspired by several people, but I kind of really got a kick in the butt from Jason Arbon. He's like, Mark, you really got to get out there and add your voice into performance and AI and machine learning so we can do this together. And so thank you to Jason for that. So I'm looking forward to his keynote. And if there's, if there any way I can sneak over into his workshop, I would do it because it sounds pretty cool. Mary Thorne's work will also be fantastic, I think. Other people I interviewed recently, there's Sue Jagosinski from Paychex, who's a first-time speaker on Agile and change. And I interviewed her. I don't think it's posted yet, but she's remarkable for somebody who had never really come to give a talk at a testing conference and is going to get on stage, but she has a tremendous amount of experience. So I'm going to try to sneak in and catch Sue's interview. Then there's so many more. Nancy Kellen, Paul Kasafi, of course, are repeat keynote speakers that are coming and still teaching and still contributing to this community. So there's a lot of cool stuff happening. I like Paul's stacking the deck. Paul always has marvelous metaphors, like extended metaphors in his talks. So I think Paul's come up with yet another one about gambling. And we talked about having STPCon in San Francisco or in Las Vegas sometime. That would be kind of cool. We might not get away with that. I don't know, the gambling part or the rest of Sin City or something. But I think Paul's talk would go over well in a casino floor.
Now, in fact, you chose some of the very favorite speakers at STP, and definitely I like the fact that some new speakers chosen each time, and they somehow come out to do a very remarkable job. So you're very, I think you did a good job by picking Sue there for the radio and for the STPCon. So good. Also, I see that you have a workshop and a session and your hot selling Perf Bites, the live podcast you do from STPCon.
Yeah.
So, and your talks are always hugely popular. So do you want to share some kind of a sneak preview to what you are going to do at our upcoming STP Con for our webinar audience?
Yeah, sure. So I'll be the session wise, I'll be it's actually, like if you're really good and a lot of people pack your room, Peggy and Rick and the folks at SDP, any conference, they really want you to come back and reach a different audience, especially if the talk can extend to even more people in different sessions throughout the year or different events. So it's the modern testing streams and teams and strategies, which has evolved as I've given the talk. I get, like you do, Smita, you get like feedback, really good feedback on, hey, could you go deeper in this part or go deeper in that part? And talk more about this particular part or that particular part.
Mhm.
So I should really rename this like even more. Like it should be like part 2, part 3, like even more modern testing teams and strategies. So this is a rework to some extent. It's still the core kind of concept for combining team structure and test strategy, which and giving a really cool kind of heuristic to be able to pull those two together, which is kind of cool. But I'm adding a bunch of new stuff about mobbing, pairing, sort of the no testing, or I'll say no ops, some of the things in the DevOps world, and where does testing actually happen in a no ops world, in a no testing world, which is a fallacy to some extent. So that'll be fun. It's just a normal session, but I hope just like the last few times I've done it, there's not an empty chair in the space. But don't let that dissuade you. You'd be very comfortable, I think, in the room. The other thing is a workshop, a hands-on kind of workshop, which is performance automation for everyone, which is expanding. Usually we teach performance testing and load testing to just a small community of really geeky, self-torturous load testers who really love performance, but we like to suffer at the hands of incompatible technology all day long. There's a lot of other people who are getting into doing performance testing if you're a developer, or getting into performance testing clearly as a functional tester, doing testing, shifting left and doing things really early in the life cycle. So the performance automation for everyone kind of talks about what kinds of automation, and there's some demos. If people want to do hands-on and kind of follow along and get set up, I'm going to be sending out a setup sheet if people want to get their machines going. It's not required to do hands-on exercises or anything like that, but you can walk through these examples with me a little bit as I show them, which is kind of fun, just to show how automation can work at different points across the life cycle, across different roles, from PMs to developers, functional testers, security testers, operations folks, monitoring folks. So that'll be kind of fun. But it's a 4-day workshop, I think, right on April 1st, which I'm looking forward to. That should be really good.
Mm-hmm. And then you have to do your perf bites too, right? The live podcast you do.
Yeah. If you've ever wanted to see how podcasts are created, and it's not an elegant thing, I'll say by any means, but it is fun. It is fun and it's funny. And if you're into performance, we have giveaways. If you remember at the last SCPCon, we gave away a pair of shoes. I'm remiss in getting this. We lost our design, so we had to design a whole set of new Chuck Taylor's Converse All Stars. So we have a new shoe design, and we'll be giving away yet another pair, and other prizes and fun kinds of things. So it should be exciting. That'll be, I believe, on Wednesday night. It's kind of an evening event, so you can come. There'll be drinks, frivolity, share some single malt scotch. Who knows what we'll do there? That should be quite fun. But it's a live webinar on the air broadcast. I guess it's not air, Smith. I think it's packets. It was just live packet streaming. Yeah.
Very nice, Mark. Thank you for all the details. And I can vouch for your sessions and workshops that they are really awesome, not just for people who know performance, but also for those who want to really know them. And in a very cool way, they are challenging, at the same time fun. And that really pushes people to learn more about performance. So looking forward to your sessions.
Yeah.
All right, so moving forward, and the quick piece of information I have for all of you here is there is an upcoming panel discussion on testing in DevOps with 3 leading testers on the planet who are known for their work on DevOps: Teresa Neat, Hilary Weber-Robb, and Lisa Crispin. Each one of these are hugely followed by testers and known for their contribution to the testing world. And this is happening on 27th of March. The link is up for you to review and register. Please do go for it. And if you are on Twitter, please share the conference information and about this webinar with your followers and connections. You can also add STP's Twitter handle to your tweets, which is @SoftwareTestPro. And you can also please note down the speaker's Twitter handle today, which is PerfSherpa. All right, so let's get started with the webinar today. A very warm welcome, Mark. We are very thrilled to have you with us today. And let me quickly introduce you for all of us here. So Mark Tomlinson is an industry-recognized performance tester, architect, and engineer. His testing career began in 1992 with a comprehensive 2-year test for a life-critical transportation system. Mark now works with some companies to make their systems faster, more scalable, and more efficient. He shares his knowledge freely via the Perf Bites podcast, a favorite at live events worldwide. He's dedicated to helping individuals and organizations adopt modern performance testing and engineering strategies, practices, and behaviors for better performing technology systems. So let me transfer the control to you now. Very warm welcome, Mark, and floor is all yours now.
Thanks, Minna. That's a very nice introduction. The audio dropped out a little bit, but the actual punchline of starting my entire testing career in transportation was that I've been preventing train wrecks for people ever since. Get it? Train wrecks. It was a train system. It's trains. It's a train joke. Maybe that doesn't go over very well, but there we go. So that I don't end up in a train wreck here myself, let's get started talking. This is my first actual webinar topic, talking about performance problems with AI, particularly artificial intelligence and machine learning. But that's not to say that I haven't been familiar with it. You may have seen the evidence of some of my influence with some of my dear friends and colleagues, Andy Grabner, who works for Dynatrace, Henrik Rexed a bit with Neotis, and a handful of other really, really smart people who are smarter than me on artificial intelligence and also integrating that with performance. So I'm hoping to talk a bit about how we approach problem solving in the performance space and where AI or machine learning will fit in, because I think that's been the biggest question that I've had over the last few months, if not years. On the subject is, I know my discipline. I know I can do performance testing and load testing, but, I hear about AI ops, ops adopting AI, and also functional test automation and other kinds of automation where there is artificial intelligence or machine learning being applied. And so I hope we can go into that a little bit deeper here, and I can help you formulate some ideas on where this is going to, how to think about it, how to adopt a perspective on the subject, and some of my own opinion a little bit, because I think I'm old enough maybe now I can have an opinion, which would be swell. So we'll talk a bit about avoiding the hype, and I hope you get that tone because I think there is a lot about Hollywood movies for the last 10 to 20 years. In fact, all the way back to 2001, you've got the computer HAL and its artificial intelligence, or one might argue almost completely self-aware and emotionally disturbed computer, all far too human of an intelligence there. But I want to bring some context to where we think about common performance problems and match them up to the performance behaviors and patterns that we already adopt and already execute. Because if you're like me, you've got 20 plus, maybe almost 30 years now of training my brain, my own artificial intelligence, my AI, which is not my I. I'll call it just my I. I've been training my own eye on performance problems for 30 years, and it's a pretty fast computer compared to a lot of other things. So, and then how do we put together some criteria to think about the benefits of using AI and machine learning within the performance context, within performance disciplines. And I want to dig into some key items there and then look at sort of 5 things that might be changed by artificial intelligence and machine learning as we move forward. As Smita really wonderfully introduced me there, I recently recoined myself the Performance Sherpa. I've been calling myself the Performance Sherpa a little bit, but not just by myself. It sort of started with this conversation with Joe Colantonio. If you guys are familiar with the Test Talks podcast and the Automation Guild, or the guilds, testing guilds, he put together this picture of me. And so I just want to keep using. Recently, I was changing my Twitter handle and some other stuff, and I'm like, that's the funniest one I've ever come up with. So I went and found that picture he made, which is hilarious, of me as a Sherpa somewhere in the Himalayas. I've been doing performance testing for about 27 years, probably 28 next year, something like that. I'm a podcaster. If you recognize my voice, I'm the voice of PerfPites, also the voice of STP Radio. I help out on a handful of productions behind many other podcasts, including Pure Performance and several others. I've been teaching, as Smita pointed out, for many, many years at STPCon and various different conferences around the world. I'm currently self-employed, currently full-time employed. I was independent for a while, and I'm working at a startup as a performance architect. They don't call me the Performance Sherpa. That's just kind of the privilege of being an old geek in networking. So I get to do that. So before we get started, and I mean that sincerely, before we get started, we're talking about AI and ML, and one of the other overarching sentiments that I get from folks is that same old sort of fear that people have that AI is going to replace us, the real corporate initiative around automating things and automating the intelligence is, well, you used to automate what I do, but you didn't automate what I was thinking, and all of the other sentiments, all the other aspects of my brain, the things I brought as a human to the table, teamwork, the dynamics for communication, feelings, beliefs, expectations, and all sorts of higher functions couldn't be automated. And now there's a potential threat that they're not just going to automate what I do, they're going to automate who I am holistically. And I am not an advocate of that. In fact, I think it's darn near impossible to get to that point. But there are lots of things similar to basic test automation that I wish I could spend less time doing. I wish I could spend less time writing protocol level correlation in a load testing tool at the transport level, because that's just a pain. And I'm not doing work that leverages my higher brain power. Maybe I am, if it's really complex correlation. But also it's communicating, influencing, really combing through and critically asking questions about the result set that I came up with, and making plausible recommendations as to what's going on or how we can fix things. So there is a bit of fear, and I just encourage you not to have fear, because that just leads you down sort of a negative way of looking at this topic. So let's just stop and think a little bit as you go on, and hopefully this talk can give you some ways to engage that conversation as you hear the evolution of this topic continue after the last couple of years. So we take a little break on that. A little primer: it wouldn't be good to talk about AI unless I sort of brought together some context for what I'm talking about. And the first off just would be the types of artificial intelligence. And one way to think about it is that it's to the customers of AI, not necessarily the types of algorithms, but sort of the way the classifications might be. It's a weak or narrow AI, which is sort of to say it's less than human capable, right? It's a very narrow focus. So you're looking at the problem space is very well defined and very narrow. And the data set that you would feed into a pattern matching machine learning algorithm would be very narrow. So here's 50,000 faces. Identify those faces to be, let's say, male or female, let's say, or non-gendered. Let's put that on a continuum of probability. Pick out people with blue eyes versus brown eyes. Very narrow, very simple. And those algorithms, nowadays with Moore's laws can run very, very fast. So weak AI, meaning it's less than human, capable, less than the human brain, human intelligence. The next category would be strong or general AI. So strong or general AI would be basically mimicking the human brain, almost indiscernible. There was a movie, and I can't remember the name of it. I just blanked on the movie, but it was a young robot that was being raised as a woman, or I guess it was fairly nondescript in the movie. And of course, there's a whole plot to it, and off the top of my head, I can't remember the name of the movie. Um, so they're basically, is it indiscernible? Can it mimic what a human brain can do? What the intelligent body, which means embodies all sorts of stuff about how human thought and cognition and interaction happens. And then there's super AI. Super AI would be going almost reaching its own self-awareness, where it can actually go beyond what human thinking is currently understood to be, and invent something new, maybe a whole new way of thinking. This was evidenced recently, perhaps a little bit within, I think it was Google that came up with an algorithm to allow computers to talk to one another, and they started inventing their own language. And I think they ended up shutting it down. I should go back and look at that story, but that's sort of the idea of super AI. And there's a lot of criticism around whether super AI could even exist, because again, you're still talking about algorithms being able to build themselves. AI algorithms themselves can be implemented in a couple of different ways. Here's a handful that I like to talk about in the recent research I did, and a little bit of this was with Jason Arbon on our conversation on the radio. One is you could consider a reactive machine, which doesn't have any data storage, but it's able to interact on a basic set of rules that you write into the algorithm to react to things. So it knows what to do given certain inputs, but it doesn't actually have memory. It can't create new memory for itself. And so it's sort of you can think of it as a memoryless algorithm. It crunches numbers and maybe executes a set of rules based on the algorithm or the biases you put in an algorithm. And that's you could call it a reactive machine. Compare that to what's called a limited machine. What maybe has very short-term memory is a good way to think of it, like a self-navigating car. It remembers sort of what were the recent speeds, what's the current GPS coordinates, what's the data about the surroundings. But if you're driving a car, most of your attention is put on what's ahead of you and how to navigate what's ahead of you. And so you may not really carry around memory of where you were. Maybe you carry around memory of the metadata. What was my mileage? What was my, what's the evidence of my travel? Maybe the little line behind the GPS that shows you where you went. But that may not be in necessarily AI. That's like logging. That's just the evidence that the AI was functioning. So a limited machine would have a limited amount of memory. And be able to use that very sort of short amount of time memory in order to interact with reality and interact with the decision engine that it's executing. A third one is called a theory of mind, and this is where I think my comment about is AI or machine learning something I should be afraid of as a performance person? Are they going to replace this cool complex stuff that I like to chew on? And so the theory of mind goes beyond just computing in terms of human mimicking, right? It gets into sort of emotions and beliefs and expectations. And the theory of mind is that there's more to the human mind or human cognition than just data in, data out. Where the other ones they call machines, the theory of mind is something you can look at in terms of, well, does anyone care? How much should we care? Do we care? And what does it mean to care about something? Is it more important? So potentially emotionally based prioritization of perspective and context would be very interesting. And the last one would be some form, like super AI, would be some form of self-awareness. And you could write algorithms, much like the Google language algorithm, to be able to interact with other AIs and develop new things for themselves, developing new algorithms. Very interesting concept. Now, taking those basics in terms of reactive minds and the theory of mind, the reactive machine, and a limited machine, and the ways of thinking about it, almost everything that I talk about in the rest of this presentation about performance will be weak AI, simply because I don't believe, and I'll hope to sort of put this out as a hypothesis, the performance problems that we deal with don't require a superhuman mind, a super AI, in order to deal with them. So the common types of performance problems that we always deal with are, well, obviously simple problems. Hey, there's poor response time. And what's wrong with that? We have some limited throughput. I can't move data fast enough. So not only is it slow, but it's related to I can't do enough of the work that I want to do. That may be a limitation of resource. So we may have problems around excessive resource usage, right? You could think of it as a limited resource or something that's using too much CPU or memory or something. And then, of course, that goes to the extreme resource cost. So we may have written a function that runs in the system, and the code, once we throw it out on the cloud, wow, that's chewing up a lot of CPU, and that costs us a lot of cycles, and that costs us a lot of money. Data storage is another one. Data storage is very expensive in the cloud, and in having a local SAN is still a very expensive thing to do if you've got a couple of petabytes of data laying around. So you're looking at extreme resource costs. That's a performance problem that we often get invited to figure out how to work on. Limited capacity for growth. So we might be able to handle the business volume or the activity today, but we're going to grow by 50%, 100%, 200% over the next year to 2 years. The classic capacity planning, right? We have a performance problem. We don't have enough growth, capacity for growth. And the other one that's more esoteric would be like missed expectations or context. Like, somebody says, oh, there's a problem, this is slow for me. This is slow because I expected something better, which is a much more, like, if you think in mind, that's more of a strong AI or even a super AI way of thinking about the theory of mind. A belief or expectation in that context helps me, wow, there's a performance problem that starts to sound like a little bit more human interaction, not just data through a machine or an algorithm. There's another range of performance problems that we define for ourselves as performance testers. So this is where I see a lot of work in AI, not necessarily focused solely on performance problems for our customers, but a lot of the AI work that's happening in performance is defined for us as performance testers or engineers, where we use AI to make it easier to find a specific bottleneck, right? We spend time gathering details about a bug, performance bug. We try to filter out through a process of deduction, avoiding or ignoring noise within the test, within the hypothesis, and what the data collection was. Well, here's noise that we can ignore. That's not the bug. The pattern we also use is around replicating those conditions in a test environment. So we're looking at what were the conditions and we're investigating something. I spent a lot of time figuring out what the exact conditions were in order to cause a bug or cause a problem or test a theory. And then again, a little bit more esoteric, we spend time escalating those issues to others. So we have to know how to communicate, gather the data, what type of personality am I interacting with to escalate that? And then also predicting when the next issue might happen. So I take everything I know and then I start thinking about the future and what are my instincts about the future and how can I predict that? And would it be valuable to predict that? So we have these two categories of performance problems and the patterns that we work in. And I say focus for this talk kind of on the right side, where we're looking at using AI and machine learning to focus on helping those patterns and behaviors work out. And so if I think about those types of work, they fall into these modes of operating, right? So first off the top of the list is the most common one, problem identification and isolation. So what is wrong, fix it, is kind of that mode of work. Something's wrong, isolate it, identify it, isolate it, and hypothesize a fix for that. The second mode of work that I see most popular in the performance world is some kind of capacity planning or trending. So tell me, how does it scale, right? What does the future look like? Can we grow? What if I do a promotion and the system gets hammered with data, hammered with activity? And then, of course, if you find out that one, there are problems that you have identified, you don't know how to fix them. Number two, they're causing capacity and problems. The third one comes up, all right, how do we optimize the system so that it doesn't have problems and that it can scale? So the third one is like another mode of work once you've kind of evolved in the process. And then kind of the last one that I end up being pulled in, this is not all different ways of working. I find a lot of people working in risk aversion. So sort of falling back to risk-based testing, the era of risk-based testing for performance. We have risk, so prove to me that the system can handle X or Y load, more of a requirements kind of straightforward test. So risk aversion or risk mitigation is a good way to think of that. So as we work in these different ways of working, problem identification, isolation, capacity planning, optimization, and risk aversion, how are we going to pull AI into those things, right? How would or could or should we apply artificial intelligence and machine learning to help solve those problems within those patterns? And we solve them for our customers. We solve them for ourselves in doing the performance work. And of course, the last one, I think it's really doing both at the same time. So if we can help, if AI and machine learning can help you to do the discipline faster, easier, more painlessly, more effectively, then end users are going to benefit because we're actually applying AI and machine learning directly to the disciplines that we execute and conduct as performance testers. So why is the market ripe then for AI to dominate, to make its way into this? And why do we find the current state of performance testing, engineering, analysis, monitoring, everything, why is this ripe for AI and machine learning as a problem space? And it's pretty clear to me. We've been talking for at least 10 years, if not more, since the birth of web services and interconnected microservices now. There's an increased quantity of disparate systems. We have more systems and they're all talking to each other. We have a diversity of systems and data about them, meaning we know about more individual systems and services, etc. And we know more from a metadata perspective about how they work, right? So we've done a good job of making individual systems more transparent, at least in the metadata space, about how things are performing and operating. So we have a bigger quantity and a bigger diversity and different kinds of data about it. We have thus a larger quantity of data for the same interval. So in a 5-minute sampling interval, according to Moore's law, we've filled it up with more data because we can, and we can process that faster, we can store it faster and retrieve it faster. And so we start handling larger and larger amounts of data in a single process space that's running, 50 gig, an app server running with 50 gigs in a single heap, whereas we would do much smaller things before. It was more expensive otherwise. And we're kind of reaching the end of Moore's law, right? And we're just that particular part. Therefore, we see announcements from NVIDIA and stuff talking about GPUs, while that's extending more of the same concept. We also have an increased scope for data analysis, meaning we want to do more work on trending and prediction in a little bit more esoteric ways or isolated ways all at the same time, because microservices are more of a federated model, if I could say it that way, where you have a scope of data analysis that looks at a transaction across a topology of services. And so the scope of analyzing not just one system, but two interdependent systems, multiple independent systems. And then you really should go back and read Jerry Weinberg's book on system thinking, because it's a remarkable way to apply that within our current problem space. Add to that, we have less time to find stuff, fix stuff. All the patterns I talked about before, less time to do capacity planning and trending. Doing an old school T1, T2, T3, take a week or 2 weeks to do capacity planning with synthetic estimations and put together those models. Putting together a model for prediction and capacity of the future, we don't have time to, you expect that to be done very, very quickly and automating that. And not that we haven't been doing that, we've been doing that for years. But the rate of change coming in is faster, which means the system changes faster, which kind of invalidates all your previous capacity planning as the code base changes, as the hardware topology changes. So those are the general challenges for performance work, and AI machine learning kind of shows up and says, hey, I can help do that faster. I can help do that, faster than you have other things to do, and you need the mean time to figuring that out is less. We need to reduce that. Machine learning, if it were truly self-aware, it would say, let me help you with the boring stuff that takes too long. So let's apply artificial intelligence to performance problems. First, proactively finding patterns of correlated measurements to help find the needle in the haystack, right? So you train an AI to find them and give you results. And I'll talk about that in the next slide. Then you might take from those results, creating a set of rules from that machine learning to construct a limited machine, not a reactive machine. We'll give it a little bit of memory, and it might be a set of rules to self-heal or automatically remediate something, right? So you have a bottleneck with limited memory. I'm going to add more memory in the heap and either dynamically, or I have to restart the service to give it more memory. Or I need to, in the VM, I need to automatically hot add more CPU because we're running out of CPU. Very simplistic rule set. Could be a reactive machine, but I would say you may put that in a limited machine so you can have it sort of remember what was the heap a few minutes ago, what was the heap currently, and start making decisions that way. Then, of course, over time, if it's a limited machine, I don't want to have to keep the plate spinning, manually by monitoring stuff. Adapt those same performance rules over time in inventing new rules for automated remediation. You could think about elastic clusters. The last time I grew during the peak interval, I grew by 200%. This time I'm only growing by 100%. So maybe my rules for when I'm elastic need to change. And so you would think about a limited machine being able to sort of adapt its own rules. That could be very interesting. And that's where that will come in. And then the other classic part, stepping away from sort of data science, where you kind of know the result you want, and you want, what kind of algorithm you want to run in order to do an aggregation or some sort of prediction in an algorithm. AI might be used to extrapolate that data into the true human experience of performance, right? Emotion, sentiment. So we may find that performance data and metadata may be used to reach sort of a theory of mind model. That's a reach. I knowingly, and my own limitations in understanding the subject space, it's a good question for Andrew Ng about that. So that would be the different ways that we might see AI be coming in and applying them to performance problems. Here's an example that you may get out there. There's a couple of them in my sources. One is like a Python, getting started with AI in 5 steps. They wrote some Python code to do it. And just training AI on images, right? So you arrange a data set of pictures of dogs, cats, birds, and fish. So you have sort of predetermined, give me 10,000 images of dogs, cats, birds, and fish. You feed that data set into the AI engine, and the engine gives, maybe it's a probability predictive algorithm that says which class of animal each picture might belong, right? Now, there's a couple things incumbent. One, you already know what dogs, cats, birds, and fish are because you have to arrange the data set. To which you might argue, if I already know what dogs, cats, fish, and birds are, the problem is I have so many pictures, I just don't want to go through them. So what I'm really solving here is I'm so overwhelmed with data, just make it easy to, don't make me go through one by one and do this manually. Automate the identification based on some artificial intelligence. So that's the problem space, is just, I don't have time to go through so much data. Makes sense, right? And of course, if you don't go through that, then you end up with a picture of a waiter with a fruit cup or a lovely, I think it looks like an eggs Florentine, some kind of an egg dish there. It's quite nice. But you'll find that picture is actually part of the Python thing. So if we take the basic steps for learning how an AI, machine learning algorithm works for predictive AI, the engine class will give you the class of animal to belong. Let's compare that kind of basic image comparison reactive model to AI on performance. Now, in performance, we're still going to arrange a data set, but we're going to arrange a data set of problems, maybe outages, with a bunch of correlated measures for CPU, disk memory, network, and response times. So that sounds easy, right? We'll just throw that together, pull a data set and throw that together. Then, of course, you quote unquote feed that data set into the AI engine, and then magically the engine gives probability for which class of bottleneck caused the problem. So if you're at the heart of hearts, problem isolation and identification being the biggest performance pattern, that's kind of the same very super oversimplified flow for how you would do that work. So you have lots of work to be done in the first step, lots of questions on the second step, and then the third step is where the magic happens. So let's talk about why that's a complex, difficult, very hard challenge. One, to arrange the data set, you have disparate measurements all over the place with different sampling intervals, different data stores, different formats of data at different levels in the architecture. And so the effort of arranging a data set for performance across a system topology is no small task. That's heavy lifting. Get the picture? Heavy lifting. There's a bunch of people kind of trying to help. They're judging him. I think they're seeing him almost fail. He's a lot like a Java server from back in Java 1.2. Anyway, so arranging the data set is more complex. And if you have data all over, performance data all over the place in all sorts of different formats, well, will AI help you reformat that? Not really. I mean, you can sort of, maybe there's some cool tool that can do data conversion to get this all in the right piece, but everyone knows we lose data when we do that. The second step is to feed that data set into an AI engine, right? Where did that come from? What was the pattern recognition algorithm that I should use? Was it a limited machine? Do I need to get into a theory of mind if we're looking at, I want to predict people's sentiments, how they feel about the experience they just had with the website? And is that how difficult is that, right? The last thing would be getting a list of correlated probability for the causes, but of course the remediation might still be disparate, complex, heterogeneously interconnected parts of larger system, e.g. Jenga. So sure, and you're getting a recommendation that the problem is this particular web service is doing something bad with CPU, but it's interconnected to so many things. To actually implement that solution might be incredibly intricate, and the Jenga tower will fall around you. So you get an idea that AI in the performance space, although it sounds like, hey, this is great, just identifying problems is a huge help. I completely agree. But if you're going to ask me to arrange all this complex data set in a way that a single or an interconnected AI engine could actually process that data set and work through the algorithm, that's hard to do. And then do I have to do that, right? Getting a list of correlated probabilities is the last piece that I might not be able to implement. And this gives a shout out to Jason Arbin's stuff. And that's just for problem identification and isolation, and not really even probability to find it. That's just one of the different patterns that we use in the modes of performance, right? There's like maybe 6 others that I could mention off the top of my head, right? So let's spend a few minutes talking about, not to leave that in the dust, I'll loop back around to that. The criteria for this is what I think we need to do to ask ourselves, do I really want to use AI and machine learning in my performance work, my performance disciplines? One is, how easy is it to configure and train the AI on a problem cogent to the performance issue or challenge, right? Is it fairly easy? I've got a seasonal trend for data. I've got some peaks and valleys and do a trending algorithm. So I could do a Holt Winters or do a few other like the profit stuff from Facebook. That's an algorithm. You could think of it as it's more of a mathematical predictive algorithm. It's not really artificial intelligence. And you do have to condition the data in such a way that the algorithm can work. So how easy is it to configure and train that AI on the data set specific to performance? That's a good question. The second thing I would ask is, are the outcomes of that product, the result of the AI, relevant to the performance problem at all? Meaning you may have found like there's lots of patterns, but then how much do I have to tune that to say, well, that's not relevant. I mean, sure, that's got a lot of CPU, but I could solve that. Like in my brain as a performance engineer, I'm like, well, that seems like the problem, but that's really a red herring. I could solve the problem with 2 other ways, by moving the traffic in a different way, having the user interact differently through the system, and we can assuage that problem, not by just throwing more CPU at a bad interactive pattern, but by actually modifying the interactive pattern itself, setting different expectations with end users, having them walk through the steps of, say, a shopping cart or some other experience differently. Pagination is a different mode, a different functional way of interacting. So are the outcomes of the AI or ML relevant to the greater performance problem we have? The other thing I ask is time savings, right? So where is artificial intelligence or machine learning going to save us time within our current operational model? So if I spend 4 hours finding things that may be wrong, and AI is going to do that in 15 minutes, well, that means I have 3 hours and 45 minutes. But if the outcome of the AI means that 3 hours and 45 minutes of time, I spent 2 hours and 45 minutes arranging a data set and maintaining the ability to pull all that data into a single store or multiple stores that are relevant, and I can query with the AI piece. So am I just trading time? I may be changing the amount of time that quote unquote the finding function is running, but I have all these other parts to the equation that now my job is changed to being a maintainer of an AI, and I don't really do performance work, and then I get bored because I like performance work and I move on. So how does that actually fit time savings wise into the operational model? Will it really save me time, or am I paying that time in some other work to keep it going? The other question is, if I get AI and machine learning running on the data sets and trends, can I use that data and integrate it with other solutions? Can I integrate it with Azure to do, or AWS to throw hardware at the problem really fast, throw CPU memory at the problem? And can it be made use of very easily, right? This is something, again, Jason Arbin talks about. Are we testing for relevance? Are we testing for implementation? So can we implement AI and ML and have it do more than just find stuff? Can it actually do the remediation? Can it trend? Can it do all of those things? Or do I have to build a whole system around several different machine learning algorithms to get that value? And does AI and machine learning help me do that? And then, of course, like with anything we build in code requires maintenance because things change, things get obsolete. That code won't even run anymore. We don't support that framework. So what overhead do we also add to keep this new thing going, right? And the overhead might also be the complexity is, do I need a PhD in mathematics, data science, and time travel in order to keep this thing running? And that's a different kind of person that and skill set that I would have experts or have to hire and maintain and keep going. So we might just be shifting that complexity and overhead. So those are the things to think about while you're thinking about AI and machine learning coming in to the system. The tools that claim a few things to avoid the hype. You might ask about tools plus AI. These are the questions that I bring up. One is transparency. Make sure your vendor can explain how they're using AI or machine learning within their products. Are they being transparent about it? Scalability, right? So if I use the tool more, does it provide more value, right? Does it recursively grow its capability over time, which means it's more valuable over time? Again, I bring up complexity, right? Do I need a PhD in math or machine learning or data science just to use this tool? And adaptability, that's the other thing, right? I may have to retrain the tool. What does it take to do that? Do I have to arrange a whole different data set? How long does it take if I have to start over completely? How much time does it take to do that? And how often must I do that in terms of adapting to change? And that's a big thing for me because my rules engine might be outdated faster than I think, and the AI can't work. It takes a lot of time to set that up again and again. Another thing I ask the tool vendors is how they test their own tools, right? So the biases within their own testing of their AI within the tool. So what data sets did they use? Are there biases within that data itself? Did they present it with optimistic data that made their tool look good? And will that, do I want to do a proof of concept for how they test those biases within their tool? And then trust, I think in the end, sort of transparency related. Do you trust the tool, right? Or is this just plain magic? I don't know how it works, but I'm just going to plug it in and use it. And this all gets to kind of avoiding the hype a little bit, because I think since we're maturing in our understanding of AI and machine learning within performance space, everyone's getting down to the nitty gritty where we have to show that it works, show that it's valuable, and show how it works as we get more mature. But to avoid that hype cycle, one, AI will replace testers. That's hype, right? Who else would it replace? Would it replace developers, operations people? It's similar to that whole test is dead thing, like which back when it came up, test is dead. Is no one else dead? Why is it only testers are dead? And why? It's a totally hollow argument, right? There's something wrong in that statement. Another statement you'll see in the hype is that we're going to accelerate the testing process. I don't think so. Maybe we're going to accelerate automated checking, data collection, data finding. Maybe there is some rapid test case creation, but boom, I have 20 million test cases. All right, it takes you 2.7 years per release to test all of them. That's kind of crazy. The other thing I might see is risk prioritization, because that gets into the sort of the theory of mind, like what is real risk and how do I feel about risk? The other thing you'll see with a lot of tools is you don't have to be an expert in performance. Anyone can use this, right? To solve all your performance problems. Anyone can use it. Really, anyone can use it? Or did we just shift the expertise to another role or profession? So we automated our performance testing, but really to understand the performance of the system, you go to another person who's not a performance tester or engineer, and you have to ask them questions that they don't even really enjoy the geekery of performance, right? So they're doing their best with their brain, which is honorable, but they're not in love with performance issues, at least in kind of the illness I have. The other thing you'll find vendors say is that the AI tool takes the painful part away from task X in performance testing, but they don't say exact how, right? What are the nuances for task X and how we do task X versus someone else? It could be, measuring CPU. Maybe there's not just one way to go camping. There's not just one way to go measuring a CPU. Is it a reliable way of measuring that? Can I measure the CPU with that same approach across disparate heterogeneous systems? And then what other pain did you create, if any, because you replace pain X on over here, but now I have this other pain, which is I need to understand a lot of math. Of course, you can also look at a tool vendor and say, is the executive team just a bunch of hedge fund managers who got funding because they used AI and machine learning in a PowerPoint deck? So you might avoid those as well. That's a dead giveaway. And to wrap things up, I just wanted to share some of my sources for this presentation and my future talks. One is Jason Arbin, so a big thank you to him for our conversation. You'll find him on medium.com. Take a screenshot of the page there, and it'll be on the recording later with the STP. Andrew Ng, I apologize for pronunciation of his last name. So Andrew was at Stanford. He now you can actually take his course at Coursera and check it, learn more about that. My good friend Andy Grabner has done a bunch of stuff around AI in the Dynatrace engine, and I implore them to follow really, really good disciplines around being an honorable, trustworthy vendor. Which is great. They do a good job. So check out Andy's stuff. He has a blog. And then a new one to me was sort of the origins of the Python image algorithm, predictive algorithm, which is Moses Olafenwa, I think, perhaps. Apologies again. And you can check out his stuff on GitHub. Just look up Moses and the image AI, which is if you wanted to get your hands on and play around with a little Python and give you a data set to do image recognition, you can see how this actually works from a code perspective, which is great. So in summary, AI is really fun. It's totally fun for finding birds and cats and dogs and fish and waiters with eggs Florentine. But when you apply it to performance, it's really hard. Performance didn't get easier because of AI. It just introduces, I think, a different kind of complexity. The benefit might be worth it to make certain parts faster in our problem identification, trending over a data set and looking for patterns, very large data sets, trending over capacity, predictive algorithms for capacity. Again, it's totally valuable, but it's more of a data science as our disciplines and profession evolves. The tools that make it look easy, It's great. It's totally worth investigating. But keep in mind the tools that actually make it easier. Ask those questions of which tools can it make it easier. Then I would really evaluate those. I would bump those up to say, well, we're investigating it, but the ones that we can actually see that actually do the work and tell us transparency how this algorithm actually works, those are worth evaluating for sure. Don't be scared of the hype. Remember that the human brain is the real I, the real intelligence, and there's a whole lot of things in even strong and super AI, or the theory of mind and even the self-awareness aspects that I don't think we're even in reaching distance of getting there, because there's always more to performance testing than just finding bugs, like anything in the testing disciplines as well. With that, I thank you for joining me. Here's some contact information if you want to follow stuff. Again, as Smita said, I'll be at SDPCon Spring 2019 in Burlingame. So there's the performance automation for everyone as a workshop, half-day workshop on April 1st. And then later that week, giving a session, even more really awesome modern testing teams and strategies. I'm going to totally put that on my slide. So thank you guys very much.
Thank you so much, Mark. It was a very insightful session on solving the performance problems with AI. And many thanks for sharing all the details. Really, it helps a lot. Let me just start taking the questions now.
Sure.
Yeah.
Happy to.
So, yes, and we don't have a lot of time, so we're going to pick quickly at least one question from all the people that have probably sent us multiple questions. Here is the first one. Without a programmatic or schema to define what an app does, how does AI know what to test?
I think it's wrong to say that AI knows what to test. I think you still come to at least weak AI, and building a reactive machine or a limited machine. It doesn't know. It calculates, I think, is the way I would prefer to say it. So you still imbue an objective upon the algorithm, upon the machine. From the impetus comes from us. Like we want you, please AI, take this data set. Remember, in all my examples, I've arranged a data set. The act of arranging a data set is sort of carries with it my intention. And so if I put together a CPU disk memory network and response time, and those are the different schema to answer the question correctly, to the idea, here's my schema, here's my landscape. I have some core physical things I know about how an app works. It uses CPU, how it uses memory, how it uses network to communicate, how it stores its data short and long term, and how much time does it take to do those things. I'm sort of bringing lower level questions to ask about how the AI should understand what the app is doing. So to some extent, classic profiling, where we maybe connect to an application and look at the methods taking up time, is one way to correlate and do that dynamic correlation based on response time. But if I feed an AI engine, here's my physical resources and here's my response time. If I feed it also method information about what methods were taking that response time and maybe what methods had certain objects of certain sizes, now AI can start making more and more correlated, looking for patterns in that chaos around a performance issue where something is anomalous, something is spiked. So it doesn't know in and of itself, but I think it calculates based on how you designed it, and then how it gets trained, meaning how it learns, hey, here's a pattern that I see a lot. There's always this response time thing here, and there's always this memory exception there, and there's always this particular method with a database call there. Okay, how do they correlate over time? And then that's a pattern that it may memorize for a short period of time in a limited machine. And so that's kind of the limit of my understanding at this point. But so I wouldn't think of it as knowing. I would think of it more as calculating, and arranging a data set sort of imbues that schema that you're presenting to the engine.
Mm-hmm. Absolutely. I think there's a reason we call it artificial intelligence, right? It doesn't have its own intelligence, and we are probably training it. So as many data passes happen, the
Yeah,
algorithm gets smarter.
yeah. There's a lot of ethical conversation out there now about how we bias the engines, how we bias the
Mhm.
algorithm that we put in there. And so testers, we do a lot of time studying things like cognitive biases within testing in different contexts. So we're actually really good at figuring out, hey, how should I test for biases within this data set? Oops, we only gave it fish that are purple. Like, what about the
Mhm.
pink fish? What about the normal gray ugly fish at the bottom? So maybe there are biases in our choices for a range. I think there's a lot of ethical gray area, no pun intended on the core,
Ab-
ironically.
abs-
Yeah,
Absolutely. So moving on to the next question, Mark, and we'll just take one more after this because we're
sure.
already running short on time.
Yes.
Here is the question. What do you consider the key differentiator in how you performance test AI, public ML work versus other types of systems? In other words, what should the performance teams be prepared for as they move into AI related applications?
So when the subject of the test, the objective of the test is an AI itself, um, then for functional purposes, you would arrange a specific data set with specific elements within the data set that would be like negative testing. In performance, you're probably looking at still what does it take to, how long does it take for that engine to be trained to a level of satisfaction? So just like we would say, I want to execute 4,000 transactions per second with a response time less than 1 second. You have some idea that the code and the system should perform its tasks with n number of volume in n amount of time. Same thing goes for AI and machine learning. How long did it take that algorithm to regress or calculate across that data set? And think about it holistically, even beyond that. Like, well, if it takes 4 hours for this application to crunch all the numbers, and we really would like it to do that in under an hour, well, that's an opportunity for performance optimization. And think about it. I mean, AI machine learning it benefits from really high throughput and really high processing instructions per second. So being able to do that really quickly and also understanding the different models. So if you're doing a reactive model, a reaction model to versus a limited model theory of mind, different capacities for storage just for that application to do its work. Where is it going to remember if it's going to have a short-term memory? Is that memory optimally located in actual physical computer memory? Or is it stored on an SSD, or is it on a disk? Is that disk type, physical medium, appropriate for the speed with which we're reading and writing, and how often that data blocks would change? So there's a lot of questions that are traditional that you might even not care about the AI or ML machine learning algorithm itself, but you're observing it and measuring it the way you would a traditional application. I think the greater scope for that is also um, in the context for what the end user expects value. So instead of just saying, yes, the AI algorithm executed, it took N number of seconds or N number of hours to run, or minutes per se. I think this is the thing the insight that again, I'll credit Jason Arbin thinking about relevance and thinking about implementation. If we can execute something really fast, is that valuable? Is it relevant to what we're trying to do? Is it solving a problem? Is it benefiting someone? And is it doing it effectively? Meaning, is it costing too much to just deliver that value back to the end user or the customer? And there may, like, let's say you're running a machine learning algorithm on climate data, and you're like, is this valuable? Well, it may save every living thing on the planet someday. Awesome. I mean, I'm not to imbue this with my own opining on on climate change, but yeah. So you have to think holistically about what's the value, and you know what, is this performing well to solve that problem, like a really really big problem that's really really valuable. Boy, maybe you go get a supercomputer and you run the machine learning algorithm on a very huge supercomputer. But if you're doing things in small scale, you know what? We shouldn't have to have a supercomputer in order to run small data set aggregation and or put together a learning model on top of it. That should be pretty fast. So think about context for the cost of delivering stuff, which is very similar to normal applications.
And we are going to take one last question, Mark,
Awesome.
and quickly try to respond to that. Yeah. And so, and there are so many coming in. So please, I'm sorry to everyone that I can just take one more. Yeah. The test environment to the production environment might differ. So how will AI ML help for performance testing? And if you can name a couple of open source tools that are available which use AI ML.
So in the open source world, a lot of the AI ML stuff becomes add-ons. So it usually runs in separate spaces. And I see a lot of work in the functional testing space and talking about sort of automating UI componentry without all of the details. I think we'll see the same thing at the protocol level when you're thinking about load testing, being able to actually apply. And I can think of a couple vendors that are working on this that I can't talk about. But they're working at, sort of patterns in the protocols so that you don't have to do all that crazy depth work. With the production to lab type of correlated work, how relevant, if I run a test synthetically or artificially in a lab, how close is it to production? I've always done this with very straightforward matching. Just what's the configuration prod, what's the configuration, what's the scale comparison between the two. With AI and machine learning, I think it might be a way to check during a test. So here are the patterns we see in prod, and run the same AI machine learning in the lab during the test. And are you seeing the same pattern? So more of a comparative application of the output, because if you ran AI machine learning for monitoring in an operation space, you're going to the machine learning given the machine being the same, it would find those kinds of patterns and give predictions. Are the predictions the same? And be able to tell you why they're different. Say, well, we predicted X, Y, and Z here, but in the lab, CPU is going to be the biggest bottleneck there. But in the lab, you actually have more CPU. Or the other way around, maybe you're like, we're predicting CPU, but we know that production has twice the CPU that you do in the lab, so we're not going to flag that prediction. And so I'm thinking there's things from an AI and machine learning that's getting into that pattern recognition for problem isolation. And again, it can be very low-level physical types of resources, or it could be applied to sort of queuing, request queuing, or different things within the app layer itself around memory management, and/or I/O as well, network and storage I/O. That could be those patterns. How accurate is my test becomes the question, comparing those two. And I could see that. I could see that being applied that way. But I think the open source tool that I see people bringing in, I've seen this used, a couple of them, with regards to tools. If you have, time series data and you pulled in measures into some kind of a store of some sort, data store, database, you can look at the profit stuff from Facebook. That's more of a trending algorithm, but they're starting, I think that's going to expand to have some more AI pieces. The guys at Netflix have a couple that they've open sourced. The other one that I'm just learning more about is the AutoML. And I can't remember I think AutoML is open source. I can double check on that. But yeah, look up AutoML, and that's the Google stuff. So Cloud AutoML is one of the things that Google, and it's actually one of the more efficient engines for getting a lot of the basic comparative matching and predictive algorithms that are out there.
All right. So I think we'll probably send rest of the questions to you, Mark, because we're still getting so many of them and the thank you notes.
Yes.
Yes.
Awesome.
Yes. So thank you so much, Mark, for your awesome session. And I'm sure our attendees found it very informative and useful too. So thank you again, and I hope to see you in San Francisco.
Thanks, Minna. Thanks, everyone. Have a great day.
Well, everyone, this concludes our webinar for today. So thank you for joining, and more importantly, thanks for being so engaging and making the most of the webinar for yourself and the whole group. If you want to see more such sessions from speakers like Mark and wish to learn more about testing, come over to STPCon Spring 2019. And do not forget to note down the discount codes and ask for the available discount offers at info@softwaretestpro.com. And stay tuned for more webinars and online trainings coming soon at softwaretestpro.com. And if you haven't yet signed up for the upcoming webinar, which is a panel discussion on testing in DevOps, with the three leading testers known for their work on DevOps, Teresa Neat, Hillary Weaver-Robb, and Lisa Crispin on 27th of March. And please go ahead and look at the link, review your abstract, and please register for it. All right. Thank you, everyone. Have a great week ahead, and see you all next month in San Francisco. And keep practicing your testing skills. You've learned a lot today on performance. Do put it to use. Thank you.